So these examples I've given are pretty general that one can do in any math course. Now I'd like to, and even in a science course really, focus more on math and sustainability, by which I mean environmental sustainability, which has become my interest over the past few years. Why sustainability? Well, one, it's an interdisciplinary topic, so there are lots of connections of math to the real world. It's certainly an authentic issue facing the world. It's really one of the great challenges of the 21st century, one of the greatest challenges ever facing humanity. And so what I'm going to do is give you examples of lessons that incorporate issues of sustainability to teach standard math material. And then I'll also talk about service learning projects that I've had my math students do that involve sustainability. At my college, we call service learning praxis. It's also called community-based learning. So a little review of what we mean by sustainability. There are various definitions, and people sometimes think it's all about the environment. But here, let's say sustainability is meeting the needs of present and future generations by reconciling economic growth, social development, and environmental protection. So certainly the environment is part of sustainability, but we also need economic prosperity, that people need to have jobs that provide a living wage. And in addition to the environment and the economy, we also need social conditions, that people need to be well treated through our society. So the challenge is how to combine these three issues in a way that supports society in the present and will also support it into the future. Okay, here I'm going to pause and backtrack back to this math and sustainability. People sometimes wonder when I mention that I'm interested in math and sustainability, how can math be connected to sustainability? They could imagine how biology and the environment and other sciences can have a link to sustainability, but they haven't thought much about how math can be connected to sustainability. So here I'm going to show that they're very natural connections, and indeed for some areas of sustainability it's hard to imagine how you could study it without using mathematics. So here I'll talk a bit about the course I teach on differential equations and modeling and how sustainability comes into that course. And I use a nice textbook by Blanchard, Devaney, and Hall, which takes a dynamical systems approach to the issue of differential equations. So it's very qualitative, and there's a lot of geometric visualization of the differential equations as compared to the more traditional analytic, where one's interested only in the formulas. And two examples I'll talk about that come up in this course are population growth and the notion of tipping points, which in mathematics are called bifurcation points. So one approach one can use in this connecting of math and science to the real world is have students read a book that has some real world interest. And I've been very interested in the writing of Gerard Diamond. He wrote the very popular Guns, Germs, and Steel, but he also wrote another book called Collapse: How Societies Choose to Fail or Succeed. This book had quite an impact on me, the idea that in the past, societies that had been very successful at some point fail and collapse, and the idea that our present societies in the world, and even our global world society as we face climate change and environmental degradation, could potentially fail. It's a very thought-provoking and sobering argument. And originally I had the students read the entire book, and for each chapter in the book, the assignment was to write a short half page to a page write-up explaining how do you see the topics from our course relate to the different chapters in the book on collapse. And this went fairly well. The students posted their writings and we discussed them a bit in class. But at the end of course feedback was that they felt that this was too extensive an assignment to add on to their differential equations course, having these reading assignments every week. So in later years I modified the assignment and I just had them read a few select chapters from the book. And one of the chapters they read was dealing with Rwanda and the genocide in Rwanda in the mid-1990s. The connection to our course is that the author discusses the fact that Rwanda is one of the most heavily populated nations in the world, and that a contributing factor in his estimation to the genocide was this overpopulation of the country. And population growth is a very standard topic in our calculus classes and also in lower level courses. You have a differential equation and the solution to it involves an exponential. So the assignment we made up, one of my students, Wen Gao, who graduated in 2007, worked on this, and it grew out of a conference we both attended at Lafayette College in 2006 on math and social justice, was taking material from the chapter on Rwanda and turning it into a population growth problem. Here I'll give you a minute to look at the assignment and the data. So here we ask standard things: what's the growth rate? What's the doubling time with this growth rate? Given the data table, calculate the growth rate, figure out the exponential solution. And then the key connection is, how does your predicted population match the actual population for 1995? And what the students find is their exponential model overshoots the population in 1995. And we ask why. And in this case, it was because that was the time of the genocide when the population was decreased, and also perhaps that people fled Rwanda for neighboring countries, and so the actual Rwandan population went down. Then we discuss the idea that we're making a model, and models have limitations. So what are problems with the exponential model? What's it good for? What does it do a good job of predicting, but what are some of its failures? So if you like, you can pause the webinar and discuss with your group this issue of modeling using an exponential function. Well, one weakness of the exponential model is that it predicts the population will grow to infinity. And we know you can't in real life have a population becoming infinite. A strength of the model is over a short time period, it does often predict the population growth fairly accurately, but only over a finite period. So that leads to our next topic in the differential equations course, the notion of a carrying capacity, that the environment can only hold a certain finite population, and this leads to the logistic model of population growth, which is written below. And the notion of carrying capacity is a key idea in issues of sustainability, and in many other fields besides math, students will learn about this. We don't actually know in a given situation what the actual carrying capacity might be, but the concept of a carrying capacity is very useful. And then we can study the solutions of the differential equations using what are called slope fields, getting this visual representation that if you begin with a large population, it will decrease towards an equilibrium solution. If you begin with a smaller population, it will increase to the equilibrium. Zero is also an equilibrium. If you start with no zero population, it will remain zero. And at least mathematically, if you begin with a negative population, it will go to minus infinity. So here we see if the population starts above the carrying capacity, it will decrease and approach that capacity. And if you have a smaller population, then the population can grow, but it limits towards that carrying capacity. We call the carrying capacity an equilibrium solution. If we begin there, we stay there. And also zero population is an equilibrium. And we can, in shorthand notation, draw this one-dimensional diagram called the phase line that shows these equilibrium solutions. Above, the solution goes down. Below it, it goes above. And if you're negative, you also go down. So we call this equilibrium an attracting equilibrium, and the zero equilibrium is called a repelling equilibrium. So this helps us analyze the situation of having a carrying capacity. This then leads into the next topic, which is having growth with a logistic equation, but then we have harvesting. And mathematically, in our differential equation, that is represented by this term minus h, that each year h members of the population get harvested. And then the question is, well, what kind of populations are we talking about? And one very important one is fish populations. And by harvesting, we mean the fish that we catch. Another example, which maybe is a little less intuitive, is forestry and logging. And the population is the population of trees. And the harvesting is how many trees do we cut down each year. So here we immediately see a nice connection of this important concept of the population growth with harvesting to real-world situations. This harvesting, we can think of examining the differential equation with different levels of harvesting. And what we'll find is that as the harvesting level changes, there are certain critical values of the harvesting level called tipping points, or mathematically we call them bifurcation values. And as we change the harvesting level past these critical values, the behavior of the population changes dramatically. This notion of a tipping point, or mathematically we call it a bifurcation, is a very important concept that has really crucial applications in our 21st century world. So I make a special effort to create some experiences for the students that will help them engage with this concept, first in a more intuitive real-world setting before we get into the mathematics. So here is this idea of trying to connect their previous knowledge about the world to a complicated mathematical concept. As we'll see, mathematically, a bifurcation point is built on 3 or 4 ideas, one on top of another. So it's a very complicated mathematical object, and I want them to come into the mathematics with some real-world understanding of it that's going to help them deal with the mathematics. So here I go back to the book Collapse, and I have them read the chapter on Easter Island. And we learned that on Easter Island, where you have the famous statues, they had a very thriving civilization, which for some reason at some point died off. And so part of the assignment is to read about Easter Island and then just write up what factors contributed to the collapse of the society. And one thing they find out is the idea that the forests on Easter Island got harvested to perhaps help move these large statues, that the trees were used maybe to roll the statues. In any case, eventually all the trees disappeared, and that caused problems for the society, which had been depending on the wood up until that point. And some of the students think, well, how silly of this society, how could they have not realized as they were using up the wood and cutting down the forest that this was going to cause a problem for their society? Next, we have a very special event in the course where we play a fish simulation game. And at the beginning of the term, I announced to the class that we're going to do this, and this is going to take 3 hours, and we're going to have a special evening meeting where the class meets to do this. And we play a game called Fish Banks, which is a study of renewable resources developed by Dennis Meadows, who is well known for the book Limits to Growth, and collaborators along with his partner Dana Meadows. And in this game, the students are in teams, and they are running a fishing company where they have their own fishing boats, and the goal in the game is for them to maximize their profit. And they take turns. Each turn corresponds to a different year. They can buy more fishing boats. They fish, they catch fish, they get income from the fishing. And what happens as the game goes on, and it's shown in these graphs, over time they crash the fish population. First they go to the deep sea where they could catch more fish. They overfish that, and the deep sea fish go to 0. Then they switch to the inshore fishing. That fishing stock lasts a little longer, and then they crash that fish. And so once they've crashed the fish, their initial profits that they made by all their fishing stops. and they no longer are making a profit, and they are losing money because they still have to pay for the upkeep of their ship. They have fallen prey to the tragedy of the commons, that individually it's in their best interest to catch as many fish as they can, but if all the different teams follow that strategy, the fish population decreases, the population will go to zero, and then they can no longer make any profit from fishing. The phenomena they're dealing with is also called overshoot, that the data they get of how many fish they catch each year, if they pay attention to that data and act logically based on that data, they will actually keep fishing beyond the point where the fish have started to decrease. And by the time they notice that there's a problem, it's actually too late to adjust course and decrease your fishing level. You've already crashed the population. And this happens in the real world. We saw that with the economic collapse in 2008, with the real estate bubble. The car industry had a crash from selling too many high-priced gas-guzzling cars, that by the time you realize there's a problem, it's too late. So the students have had this profound experience of themselves overfishing, and they realize that they, just like the Easter Island people, can easily fall prey in the moment to using more resources than will last in the long term. So here I've set the stage for now the mathematics of this overpopulation and crashing of population by this real-world experience. So the mathematics involved is something called a bifurcation diagram. It's made up of a bunch of these phase lines, these vertical lines that we looked at earlier, and for each different fishing level, you have one of these vertical lines. I have the students in teams do a jigsaw exercise where they each have a couple of H values, and they draw their phase lines for those H values, and then the other teams put in their phase lines, and together we produce this whole diagram, and we kind of connect the dots of the equilibrium to get what we call the bifurcation diagram. And the key point is that there's a critical level, which we can call the tipping point or the bifurcation value, beyond which the fish population crashes to zero, and below which you have an equilibrium value, and the fish population could stay at that steady state value forever, and one could fish profitably at that level without ever crashing the population. So here we can see how mathematics can help us understand a real-world situation, and going forward one could, for example, try to help the fishing industry regulate itself by using this notion of tipping points or bifurcations so it doesn't crash the population and put all the fishermen and fisherwomen out of business. So here we see this issue of the critical fishing level. One takeaway is that if you're near a tipping point, what would seem to be a small change in the system, increasing the fishing level by just a small amount, can actually have a drastic impact on the outcome. You can go from a steady state level to crashing the population.